Good day, students. In this clip, we're going to be going over how to solve systems of linear equations by the method of elimination. That method is also known as the method of linear combination. More clips can be found on math.serve.com, so you can always go there to find a selection of a wide variety of tutorials. Before we get started, let's take a look at the possible solutions that you can have when solving a system of equations by elimination. So let's title this possible solutions. Possible solutions. Okay, so when you're solving systems of equations involving three variables or a 3 by 3 system, you can expect to have one unique solution, infinitely many solutions, or no solution. Okay, so these are the three cases here: one unique solution, infinitely many, or no solution. An example of a unique solution is when you have definitive values for your three variables. Okay, so let's say you solve the equation and you end up with a unique value. You have an answer for all three variables. So for example, 1, 2, and 3. If that's your answer, that means that the three planes intersect at a point, namely 1, 2, and 3, and a point alone. Okay, so this is a graphical example of one unique solution. You can also have infinitely many solutions where the three planes intersect in a line. So how do you know um, when you have a situation that involves infinitely many solutions? When you end up with an identity, okay? An identity, a statement that's always true. For example, when solving an equation, you end up with something like 4 equals 4. That is always true. The variables basically cancel out and you end up with an identity of this nature. Then you know that you have infinitely many solutions, all right? Now, how do you know that you have no solution? No solution happens when the three planes do not intersect at a point. You see this case? Um, the, how the planes intersect, they intersect at three different lines and they never intersect at a point. And here you can see that they do not intersect at all. These two planes, the blue plane and the green plane, never intersect. And here you have three parallel planes. So these are the three possible cases where you have no solution. Now, how do you know that you have no solution when you're solving it? Solving a system of three equations when you end up with a false statement. What is an example of a false statement? If you solve an equation and you end up with something like 2 equals 3, is this ever true? The answer is no. This is a false statement. Okay, so let's go ahead and take a look at the steps that we're going to use to guide our problem solving process. So we will call this, let's say, steps. So first, you have a 3 by 3 system. What you want to do is you want to reduce your 3 by 3 into a 2 by 2 system. Okay, so reduce your 3 by 3 system into a 2 by 2. And then next, you will solve the resulting 2 by 2. You solve um, the 2 by 2. All right. Remember, a 3 by 3 can be considered as three planes, right? And then a 2 by 2 is just two lines. Okay. So you're gonna get a pair of coordinates here. After solving your 2 by 2, you're going to use the solution from your 2 by 2 to find the final answer from the 3 by 3. All right. Use your solution from 2 to find your answer, your answer, actually your third answer. Let's just call it the third answer. To find your third answer using 1. Okay. Your, to find your third answer, by substituting in 1. All right, so you solve your 2 by 2, you have 2 answers, but this is a 3 by 3, which was reduced, so you have to find the third answer, and that's normally determined by plugging in your answer from step 2 into your original equation, which is a 3 by 3 system, okay? All right, so let's go ahead and apply these steps to 3 examples. So let's take a look at problem number 1. The instructions are to solve the following systems. Solve the following systems by elimination. There are other ways that you can solve this, like using matrix graphing or graphing, but we're just going to use elimination or linear combination in this tutorial. All right, so for problem 1, we have the system 2x minus 6y plus 2z equals 18, x plus 2y plus z equals 9, and then the third equation is negative 3x plus 3y minus 3z equals negative 27. Okay? All right, so to solve this system, we want to find the value x, y, and z that satisfies all 3 equations. First thing we're going to do to keep our work organized is label the 3 equations. Okay, I'll label the first equation 1, the second equation 2, and the third equation number 3. Okay, now we have a 3 by 3 system. We would like to reduce it into a 2 by 2 by eliminating a variable. So we can either eliminate x, y, or z. So which is the easiest to eliminate? Well, what you want to do is you want to look at the coefficient of the x's, the y's, and the z's. Whichever one has a coefficient of 1, that's normally easy to eliminate. Well, why is that? Well, it's easy to create an opposite if its coefficient is a 1. Okay, so let's look at equation 1, 2, negative 6, 2. None of them are 1. Equation 2, 1, 2, and 1. Well, we have 2 good candidates here, the x or the z, since they both have a coefficient of 1. All right, and then in equation 3, negative 3, 3, negative 3. None of them have equation of 1, a coefficient of 1, so we can use that. Now from equation 2, we can pick one variable to eliminate, x or z. Let's eliminate x, okay? So how we will do this is we'll pair up 2 equations at a time and eliminate the variable x, okay? So we can pick any combination of 2 equations, 1 and 2 and 2 and 3, or 1 and 3 and 2 and 1. So any combination, there are 3 possible combinations that you can form here. So just pick any 2 and eliminate x, okay? So let's, how about we start by picking 1 and 2. So from 1 and 2, what we're going to do is we're going to eliminate x. So let's go ahead and extract equation 1. 2x minus 6y plus 2z equals 18. And then let's extract equation 2. X plus 2y plus z equals 9. Now to eliminate this by linear combination, we want to create opposites with the x's. This has a 2. What is the opposite of 2? Negative 2. So you see the beauty of having a coefficient of 1 here? By simply multiplying by negative 2, I can arrive at the opposite. So I will multiply the second equation by negative 2. Okay? So this system becomes, the first equation stays the same, 2x minus 6y plus 2z equals 18. And then the second will distribute negative 2. We have negative 2x minus 4y minus 2z equals negative 18. Okay, so what we'll do now is we'll combine these two, and x should be eliminated. Okay, so let's go ahead and combine it. When we combine it, we'll have these x minus 2x is 0, negative 6y minus 4y is negative 10y. These are opposites, they add up to 0 also, and this is equal to 0. 18 minus 18. Now we'll divide both sides by negative 10 to get the value of y. We will end up with y equals 0. Now this is equation number 4. Remember, we want to set up a 2 by 2, okay? This one's supposed to have y and z since we eliminated x, but it just so happens that z got eliminated along with our elimination of x. It does happen sometimes. Okay, so we have one equation down. Now we selected 1, 2. Now we can either select 1, 3 or 2, 3. We want to use equation 2 again because we determined that x has the coefficient of 1. So we do 1, 2 and 2, 3. So next we're going to go from 2 and 3. What are we eliminating? We're going to eliminate the same variable. Okay? We want to change it from an equation in xyz to an equation in just yz. Okay? So we're going to eliminate x again. So let's go ahead and write down equation 2. Equation 2 is x plus 2y plus z equals 9. And then equation 3 is negative 3x plus 3y minus 3z equals negative 27. Okay, so let's see. We want to create opposites with the x's so that we can eliminate them upon combining the two equations linearly. So this is negative 3. So what is the opposite of negative 3? Positive 3. So by multiplying the first equation by positive 3, we can have opposites with the x's, and then we can eliminate the x's by linear combination. So what we'll do is distribute this 3 to every term here. So if we do that, we're going to have 3x plus 6y plus 3z equals 27. And then the other equation, equation 3, remains unchanged, negative 3x plus 3y minus 3z equals negative 27. Okay, now we'll combine these two equations linearly. When we combine them, we'll have this adds up to 0, this adds up to 9y, this adds up to 0, and this adds up to 0 also. So here when we divide both sides by 9, divide by 9, divide by 9, we will have y equals 0. And this right here is equation number 5. So now we're going to set up a system of equations using 4 and 5. So let's write down what we are going to do. Form a system with 4 and 5. Remember, the goal is to reduce the problem from a 3 by 3 into a 2 by 2. Okay, we're not solving a 2 by 2 equation here. This is a 3 by 3. Okay, so now we have y equals 0 from equation 4 and y equals 0 from equation 5. Remember, these are two different equations. They're not the same. Okay, so what I'm going to do is I'm going to make a substitution. I'm going to substitute 0. Let's call this equation 4. And then this is equation 5. I'm going to substitute 0 for y in equation 5. Okay, so let's go ahead and do that. So let's substitute 0 for y in equation 5. So let's do that. If I plug in 0 for y in equation 5, I'll end up with 0 equals 0. What is this? This is an identity. All right. So remember, we talked about this earlier. When you have an identity situation, that automatically means you have an infinite number of solutions. So infinitely many solutions here. All right, let's take a look at what this looks like graphically. All right, so let's take a look at the graphs of the three planes. So the first equation, let's graph that. There goes the first plane right there. So that equation number 1 is represented by this plane. The second equation, equation 2, let's graph that. Now, the intersection, you see that line right there? This line represents the solution to equations 1 and 2. You notice how we have infinitely many solutions because there are infinite number of points on this line that represents the intersection of the two planes. Now let's go ahead and graph the third equation. Equation 3, the third plane. Boom. You see that? All three of them intersect on a line. So how many points are on the intersection of the three planes? Any point on this line, and we know that a line contains an infinite number of points, so we have an infinite number of solutions. Okay, so this is a graphical representation of a situation where you have an infinite number of solutions.